The ends of linear chromosomes pose unique problems during DNA replication. Because DNA polymerases can only elongate from a free 3' hydroxyl group, the replication machinery builds the lagging strand by a backstitching mechanism. RNA primers provide 3' hydroxyl groups at regular intervals along the lagging strand template. Whereas the leading strand elongates continuously in the 5' to 3' direction all the way to the end of the template, the lagging strand stops short of the end. Even if a final RNA primer were built at the very end of the chromosome, the lagging strand still would not be complete. The final primer would provide a 3' hydroxyl group to synthesize DNA, but the primers would later need to be removed. The 3' hydroxyl groups on adjacent DNA fragments provide starting places for replacing the RNA with DNA. However, at the end of the chromosome, there is no 3' hydroxyl group available to prime DNA synthesis. Because of this inability to replicate the ends, chromosomes would progressively shorten during each replication cycle. This end replication problem is solved by the enzyme telomerase. The ends of chromosomes contain a G-rich series of repeats, called a telomere. Telomerase recognizes the tip of an existing repeat sequence. Using an RNA template within the enzyme, telomerase elongates the parental strand in the 5' to 3' direction and adds additional repeats as it moves down the parental strand. The lagging strand is then completed by DNA polymerase alpha, which carries a DNA primase as one of its subunits. In this way, the original information at the ends of linear chromosomes is completely copied in the new DNA.